One important application of the operational amplifier is this D to A converter. Now we'll be discussing two methods to do this, to perform this operation, wherein the first one is binary weight resistor method. Now don't be afraid after seeing this circuit. It's very simple circuit. Only thing is the switches here. The switches here make it look complex, okay, but that is pretty simple to understand. Now here these resistors are called current scaling resistors, because you see, when you find the current, as I have done here, suppose this is I1 here, I2 here, I3 here, and so on. I have only shown this circuit for 3 bits. You can call this bits actually, B1, B2, B3. These are nothing but the bits of the digital input, suppose. Okay, so this is the sum, the total current here, IT, will be the sum of all these currents, right? So this current will only come when this switch is closed. These switches are closed. So suppose you want to give 1, 1, 0, then close these two switches and open this switch. Fine. Okay, so next just write down. Now this is nothing but a inverting amplifier, right? So what's the formula? This total voltage, output voltage will be equal to, this is also IT, so output voltage will be equal to minus IT into RF. So if you write IT here, this is the bits, these are nothing but 0 or 1, 0 or 1, whichever is there you have to consider. Okay, taking R common, you will get this. Now here if you write RF equal to R, you are going to get, this is nothing but a binary sum, right? So the output will always be proportional to the bits. This is nothing but weights of 2, powers of 2. So that is why it's also called a weight resistor method. Okay, now suppose take this only. If you want here the output, now what will you get? These two will be present and all else will be 0. Okay, so you can calculate the output for each value of the binary input, that is digital input. You are getting an analog output. So this is a weight resistor method. Now, and here I have also generalized this case. Remember, the circuit diagram I have shown only for 3 resistors, but this is a general case for n different values. Okay, now this method has a major drawback. What is the drawback? Means you need resistors of all powers of 2, 2R, 4R, 8R, and so on. Now it's very difficult to find these resistors in the market because you don't get such accuracy in the resistors. So that is a major drawback. Next is the switch resistance. These switches which we are using here, they will offer some resistance. Due to this resistance, these values which we have, this formula which we have calculated may not be accurate. Okay. Now the second method which we will discuss is a inverted R2R ladder. It is called inverted R2R ladder. Okay, and you will know why. First thing is because this is in the form of a ladder network. Here one resistor, here, here, here. So this is in the form of a ladder network, and the resistors are R and 2R. So it's called a R2R ladder. Okay. Now here if you observe, there are only 2 types of resistances, R and 2R. So this is the advantage. The resistor problem is eliminated, which we had earlier. Okay. Now note that these are the voltages at points A, B and C. I have shown here A, B and C. Okay, so these are the voltages. This can be calculated using the potential divider formula. Okay, now here also I have shown only 3, but this can extend up to any number of ladders. Okay, now here see I1, same, the currents are here also. You have the switches and the same thing, I1, I2 currents, and this will be IT, total current. Okay, so here see I1 is nothing but VA by 2R, I2 is VB by 2R, I3 is same VC by 2R. So these are the values you will get if you substitute in this is also same. This is also like a inverting amplifier. So if you substitute in the formula, you will get again the same thing. So again you substitute R is equal to R, finally you will get the same thing. So this is also essentially the same method, with the only advantage that this problem, the resistor problem, has been eliminated by using only 2 types of resistors. Okay, now let us go to A to D converters. till now we have discussed D to A. Now let us go to analog to digital converters. Now in these there are 4 methods. Okay, I'll discuss all them one by one. In this lecture we will discuss only the first one. In the next lecture we will discuss the other 3. Okay, now the first thing is called single slope ADC. I'll tell you why it is called a single slope ADC. Here initially these counters are set to 0. Okay, the whatever is the number of bits, all are set to 0. This RAM generator is also initially at 0 point. Now what happens is, when this input is applied, now suppose you apply some input, suppose like this, suppose like this you apply. Now till initially the ramp is 0, right? So see this graph, initially the ramp is 0. So till the ramp reaches here, this output of the, this is a comparator, remember. See, this output of the comparator will be positive, logic 1. Okay, now when this is since this is AND gate and this is logic 1, this clock will be transmitted as it is, whatever it is, this clock will be transmitted like this, and with each clock pulse this counter will increment. It keeps on incrementing. So it's like this. This keeps on incrementing, and till when this continue, till the ramp reaches this point. When the ramp reaches this point, what happens? This counter stops because this clock pulses stop coming, so counter stops at that value, whatever value that is. And at the same time this RAM generator is reset, because it gets this timing device gets a signal that this has gone low, so this is reset, and this counter transfers values to output where it is latched. The values are latched, that means values are stored, and later they can be, here you can also connect a display, so they can be displayed. So got the point? Okay, so remember this circuit and remember this diagram. From this diagram you can explain. After this again ramp will start from here, because again here it is reset. Okay, next, the drawbacks of this method are less resolution. See, what do you mean by resolution? Resolution is nothing but the smallest value of input, that is analog input, that can be detected. So less resolution in the sense very small values cannot be detected. This is the reason is because this ramp is not very accurate, right? You will see in the second drawback that this ramp has got some variations with temperature, with aging and all, so this won't be very accurate. So due to that, less resolution is also a problem. Okay, the next lecture we'll discuss about the other methods.